Today we're going to look at lesson 4.4, which is adding and subtracting rational expressions. If you think back to the last 2 weeks, we dealt with lesson 4.3, which was just multiplying and dividing rational expressions. So this is just going to kind of round out the whole process here with 4.4, and then we'll actually be solving rational equations in the next lesson, 4.5. I kind of want to start this off with just really taking the Algebra 2 level concept that we're learning here today and backing it up to, well, very similar to what they're doing up here in this critique and explain idea. And just kind of jog people's memories about when you add or subtract fractions, what needs to be present. A lot of people hate fractions, right? I know a lot of people call them the F word just because that's how much they hate them. There's just certain properties that apply with fractions that you got to remember, and we're going to take a look at those today. So it doesn't matter if you're adding or subtracting fractions, there's similar properties that happen, either adding or subtracting them. If you think back to the last lesson, 4.3, when you multiply and divide, you can multiply and divide any fractions. It's kind of game on when you're multiplying and dividing. Nothing really has to be in place. There doesn't have to be specific things happening, right? It's just you can take any two fractions, multiply and divide them, and you keep moving forward. When you add and subtract, that's a little bit different. So let's kind of break this down to, a simpler idea. So how about 2/3 plus 7/3? I can just add these fractions as they sit, which would give me 9/3, which again reduces down to 3. So let me kind of walk you through what happened here. So I've got two fractions, two rational expressions. I can't reduce them right now. They're just 2/3 and 7/3. It's not like they can reduce down and simplify, so they are what they are. But they're set up right out of the gate, ready for me to add these two fractions because of this. Both of my denominators are exactly the same. That's key. If you want to add and subtract fractions, your denominators between those two fractions has to be identical. Not almost correct, not, almost there. They have to match perfectly. And again, in this example, which is, back to elementary school or whenever you learn adding fractions, your denominators are both threes. So this is how it works. I'm going to take my numerators and I'll actually add them together. So 2 plus 7 is 9. But look at my denominator. Notice I didn't do 3 plus 3 is 6, right? If I'm adding or subtracting two fractions, as long as they have a common denominator, I can do that. But just the numerator gets added. The denominator stays the same. So if I take 2/3 and I add 7/3, I'm going to have 9/3. That denominator doesn't change. And then the last step, this just happened. I just pulled these numbers out of thin air. So we were able to simplify this. 9 divided by 3, 9/3 is the same thing as 3. All right. Let me give you a different situation where there's going to be a little bit more work. So there's the first example. As long as your denominators match, you can add and subtract fractions all day long. If I give you something like 2/7 minus 4/3. In this case, my denominators are not the same, so I can't just subtract these two fractions the way they sit. I'm going to have to kind of manipulate this expression and rewrite these two fractions to force them to have a common denominator. So what I'm looking at is still my denominator. I don't really care about my numerator. I don't care which numbers are up top. My whole goal here is to make these denominators match, okay? So I'm thinking, and they call it in this section, the LCM, the least common multiple. So I'm trying to figure out what is the smallest number that both of these denominators can go into. Well, my multiples of 7 are 7, 14, 21, 28. What's next? 7 by 5 is 35, and so on. What about my multiples of 3? 3, 6, 9, 12, 15, 18, 21, 24, and so on. So I'm looking for the smallest number that both of these numbers can go into. Well, there's a 7 over here. There's no 7 over here. There's a 14 over here. No 14 over here. There's a 21 over here and a 21 over here. So based off of that information, I think my least common multiple is going to be 21. So the thing is, though, what do I have to multiply these two fractions by to get 21? Well, 7 times 3 is 21. So I'm going to multiply the bottom by 3. But don't forget, I've got to multiply the top by the exact same number. If I multiply the denominator by 3, I've got to multiply the numerator by 3. So what does that give me? 3 times 2 is 6. 3 times 7 is 21. And then now the second fraction. My denominator is 3, but like I said, I want that to be a 21 because that's the least common multiple. So 3 times 7 is 21. So if I multiply my denominator by 7, I've got to multiply my numerator by 7. So my second fraction, 4 times 7 is 28. 3 times 7 is 21. Now look at what we've got. We've basically got the same situation we did up here with this example. We've got common denominators. They match, so I can just add my numerators. So 6 minus 28 is negative 22. My denominator is 21. So that would be my final answer. Will you always have to multiply both fractions by something? No, it just kind of depends, right? There's a lot of different situations. Let me leave that one up there. Let me think of one. How about 3/12 plus 1/4? Okay, 3/12 plus 1/4. Again, I can't add these. It's not like it's going to be 3 plus 1 is 4, 12 plus 4 is, 16. It doesn't work like that. You've got to have common denominators. So with these, I'm going to do the exact same thing I did up here. For my first denominator at 12, I'm just going to list out a few multiples of 12. So 12 times 2 is 24. 12 times 3 is 36. 12 times 4 is 48. And so on. You could keep listing them out if you wanted to. What about my multiples of 4? 4 times 1 is 4. 4 times 2 is 8. 4 times 3 is 12. 4 times 4 is 16. And so on. And the reason I stopped is because I'm already seeing a common multiple, a least common multiple. I think my marker's dying. So they both can go into 12. So since this denominator is already a 12, I don't have to do anything to it. I don't have to multiply anything by it because the denominator is already what I want for my least common multiple. But then the second fraction, if I want that denominator to be a 12, I'm going to have to multiply 4 times 3. If I multiply the denominator by 3, I've got to multiply the numerator by 3. It's got to be the same thing. Because technically what I'm doing here is I'm taking 1/4 and I'm multiplying it by 1. 3 divided by 3 is 1. I can take any number, any fraction, anything, and I can multiply it by 1, and it doesn't change that number. It just changes what it looks like. It's still the same number. So 4 times 3 is 12. That's my denominator. 1 times 3 is 3. So now I can add my numerators. 3 plus 3 is 6. And again, don't forget, when you're adding these fractions, the denominator stays the same. So that can reduce down to 1/2. So those are 3 situations that you're going to see in Algebra 2. The first example is where your denominators are already alike and you're good to start adding or subtracting. The second one is something like this, where one of your denominators is already the LCM. So it's already the least common multiple. You just have to multiply the other fraction by something to get that common denominator. And then the third example is where both of your fractions have to be multiplied by something. It doesn't have to be the same thing. This is multiplied by 3/3. This is multiplied by 7/7. So you can multiply those two fractions by different things. But again, your whole goal is to make sure your denominator is similar. It's exactly the same between both fractions. All right. Well, like always, that is just kind of an intro to what we're doing with this lesson. Of course, we're in Algebra 2, so this material is going to get a little bit nastier, right? But don't overthink it. Just keep that idea in mind, just like the examples I went through. I can't add these three fractions together because they don't have common denominators. So I'm going to have to multiply 1, 2, or maybe all 3 fractions by something to force them to have a common denominator. So that same method is still going to happen when we work through these example problems. All right. So example number 1, add rational expressions with like denominators. So this is starting you off with the easiest of the options. If you look here, these 2 fractions have common denominators. They're exactly the same. This is x plus 4. This is x plus 4. If this was x minus 4 and this was x plus 4, then you couldn't add them together because those are separate. But if you look, these 2 denominators are exactly the same. So what I could do is I can add my numerators. I think I'm going to go ahead and write this out just so I can work through. I feel like it's better when I actually do the problem for you. So I've got x over x plus 4 plus 5 over x plus 4. All right. So like I said, our denominators are exactly the same. That's kind of what I'm looking at. So since they are exactly the same, I can go ahead and add my numerators. So I'm going to take the x, I'm going to take the plus, I'm going to take the 5, and that's all in my numerator. And then remember my denominators, if I'm taking something divided by x plus 4 and I'm adding something divided by x plus 4, it's going to give me a sum of something divided by x plus 4. All right, those 2 don't change. It's not like I have 2x plus 8. I'm not actually adding my denominators. It's just going to stay the same. Just a little notation thing. I like to do this, but it's up to you. I like to put parentheses around things. You can leave it like this, or you could put parentheses around it. It's completely up to you, but either way, it's correct. All right. So, and that's exactly what they did here. They simplified the numerators, and they just kind of re-emphasized when you add the 2 fractions, your numerator adds together, but your denominator stays exactly the same. B is a little more interesting. So let's take a look at B. 2x plus 1. Okay. And again, if you want to look, through this example, you're more than welcome to walk yourself through it as I talk about it, but it's up to you. So with B, the first thing I'm noticing is that these 2 things are seemingly not the same, right? They don't look the same. Just by looking at them superficially, there's an x squared plus 3x, there's an x times x plus 3, excuse me. So just visually, they don't look the same. So your first thought might be, well, I can't add my numerators together because my denominators aren't the same. But remember, throughout basically this whole year, we've been talking a lot about factoring, taking the GCF, the greatest common factor, and factoring things. So you can go one of 2 ways. I can factor this quadratic, and I think that's the way I'm going to go. So I could still have my numerator as 2x plus 1, and my denominator, both of those terms have an x in them, so I can take a GCF of x out. If I had 2 x's and I took 1 out, I'll have 1 left over. If I had a 3x and I took 1 out, I'll just have a 3 left over. Don't forget this idea of taking a GCF. All you're doing is dividing these terms by x. If my GCF is an x squared divided by x is x, 3x divided by x is 3. And now when we look at this problem, at least the rest of it, look what I have on the other side. Now, my two denominators match, okay? So at first, they visually didn't match, but I was able to manipulate one or the other denominator to make them match. Like I said, you could have gone this direction where I take the GCF and factor them apart, so they're both factored, or I can go the other direction, 2x plus 1 over x squared plus 3x plus 3x minus 8, 3x minus 8. And in this case, I'm going to go ahead and distribute that x. So x times x is x squared. X times 3 is 3x. And like I said, just like over here, when I factored them, I have common denominators. And then over here, when I distribute that x, I have common denominators as well. Either way you want to go, it doesn't matter. It's completely up to you. Let's see what the book did. It looks like the book distributed, and they distributed that x, and they got a common denominator of x squared plus 3x. So, but again, I'll go this method, and we should get the exact same answer at the end. Let's go ahead and check it out. So because both of our denominators have, they're exactly the same, this is what I like to do. I like to combine both of those fractions as one single fraction. So my denominator, if it was x times x plus 3, and the second denominator is x times x plus 3, then the new denominator should be x times x plus 3. But just like we did up in A, I'm going to take the first numerator. I'm going to add the second numerator. And then at this point, now everything is kind of in its place. Now I can just add like terms. So I've got a 2x plus 3x, so that's a 5x. I've got a 1 minus 8, so that's negative 7. And in my denominator, x times x minus 3. There's nothing else I can do. There's nothing I can factor. There's nothing I can GCF out. There's nothing I can do to simplify this fraction overall. Keep in mind that yes, there is an x up top and an x down below, but I cannot cross those out because the only thing I can cancel are factors, things that are being multiplied. This 5x, right, we're subtracting 7 from the 5x. It's not like it's 5x times something. In that case, then I could cancel out the x's. But in this case, they're subtracting 7 from 5x. So because I'm adding or subtracting something to that term, I can't cancel those out. So that would be my final answer. Let's double check and make sure the book says the same thing. Yep. And then the other thing I want to mention is make sure you're looking out if they're talking about domain restrictions or anything like that. If they wanted a domain restriction, kind of like we've talked about in the past, you'd have to figure out when your denominator was going to equal 0 and then restrict those numbers. But it doesn't look like they're looking for that here. All right, so we're on page 218. Get this in the center for you. Okay, example 2, identify the least common multiple of polynomials. And this is kind of what I was emphasizing in that example in the beginning with this. The example we just looked at had common denominators, but once you're down to the other two examples, they do not have common denominators. So what we did was we multiplied both fractions in order to come up with the least common multiple, okay? Some people like to just come up with common multiples. It doesn't have to be the least or the lowest number, because then you're just going to reduce later on. But I'd always shoot for the least common multiple, and it's less work that you have to do later on. Can you find the least common multiple of polynomials? So let's take a look at this. X plus 2 squared, x squared plus 5x plus 6. So this question's a little bit weird, but imagine this is like two separate fractions. So you can imagine it like this, like 1 over x plus 2 squared plus 3 over x squared plus 5x plus 6. So it doesn't outright tell you that, but that's what you're doing here. You're taking two expressions and you're trying to figure out what the least common multiple is if they were in the denominator. Okay. The first thing that it's telling you to do is make sure you factor. I think I emphasized this last week. Factoring is something we've been doing for a long time, and it's something you will continue to do for a long time, not only in this class, but in pre-calc and other classes as well. So when you hear the word factor, make sure that your brain is going towards, depends on the method you're choosing. Slide, divide, bottoms up. Some people use the box and cross method. It just kind of depends on what you found out worked for you. I like the slide, divide, bottoms up, and that's what I'll show you here. So this first denominator, if you want to call it that, that's already factored, right? There is no quadratic here. It's not like it's x squared plus 2. It's just x plus 2 squared. And another way to write that is x plus 2 times x plus 2. This is just kind of a shorthand way of writing it. The second expression, that is a quadratic, x squared plus something or minus something. If you have an x squared, that means it's quadratic and you can factor it. What I like to do was the slide, divide, bottoms up. So let's check this out. So up top, a times c, 1 times 6 is 6. Down below, b is 5. I need two numbers that multiply to ac, and the same two numbers have to add to 5. So I think in this case, it's going to be 2 and 3. 2 times 3 is 6. 2 plus 3 is 5. So I think those are my two numbers here. With slide, divide, bottoms up, you'd always go back and divide by a, but in this case, a is 1. So if I divide by 1, nothing changes. It's still a 3. It's still a 2. So that's a positive 2. So it's going to be x plus 2. That's a positive 3. So it's going to be x plus 3. And now again, think about this as two different fractions. 1 over x plus 2 times x plus 2. And then 1 over x plus 2 times x plus 3. Okay. You need a common denominator. Your denominators have to be exactly the same. So what's different between these two fractions? What's different when you look at what the first denominator has versus what the second denominator has? So in this case, the first denominator has 2x plus 2's. The second denominator has 1x plus 2. So what we're going to have to do here is over here with this fraction, we're going to need another x plus 2. That's all that means. We're just going to need another one up there. So maybe I'll just delete that. I don't want to confuse anybody. So I'm going to need another x plus 2. This fraction had 2 x plus 2's. This one only had 1. So I'm going to need another x plus 2 up here. This second fraction has a denominator of x plus 3. There are no x plus 3's over here. So this fraction is going to need an x plus 3. So if I did that, right, if these were fractions and I multiplied the denominator by x plus 3, I would have to multiply the numerator by x plus 3. But technically they're not. We're just looking for the least common multiple between both of those expressions. So that's what I started off with, an x plus 2 and an x plus 2. Over here was an x plus 2 and an x plus 3. In order to make these match, I'm going to need two x plus 2's and an x plus 3. So the new thing on this first fraction is the x plus 3. Over here, I already have an x plus 2 and an x plus 3. So the new thing I need for the second fraction is an x plus 2. So I think the least common multiple between these two expressions, between these two fractions, it's going to be x plus 2 times x plus 2 times x plus 3. Again, you could shorthand that a little bit, x plus 2 squared times x plus 3, but that would be my least common multiple. Part B, so looks like I've got a few things over here. So for part B, I've got x cubed minus 9x. I've got x squared minus 2x minus 15. And then I have x squared minus 5x. So the easiest way to approach these is to always factor, take the GCF, factor everything. And then basically we're looking to see which factors are missing between all three of these things. So my first, let me switch color. My first problem, x cubed minus 9x, there's a GCF. You're always looking for a GCF first. So if I GCF out an x, I'll be left with x squared minus 9. And then I have x squared minus 9. So I can solve that. I'll just do it right underneath it. X squared minus 9 equals 0. This is one of different methods you can do this. I'll add 9 to both sides. Hopefully you remember this. And then I'll square root both sides. So I have x equals positive and negative 3. Don't forget when you square root a number, you have the positive and the negative version. So I still have the GCF that I took out in front. If my x values are positive and negative 3, I'm going to have an x minus 3 and an x plus 3. Make sure you're with me with that, right? If I have x minus 3, what value is going to make that equal 0? Well, that would have to be a positive 3. 3 minus 3 is 0. So there's my positive 3. And then for x plus 3, that would be a negative 3. Negative 3 plus 3 is 0. And there's my negative 3 right there. So it's pretty much the opposite signs. So there are my three factors here. X, x minus 3, x plus 3. So let's see what else we got. With this second expression, I think it's set up for me to factor. So a times c goes at the top. B goes at the bottom. Two numbers that multiply to negative 15, and those same two numbers have to add to negative 3. 5 and 3. Let me see if I wrote that down right. Negative 2. So let me correct this real quick. So this is negative 2x. There we go. So this is a negative 2 down here. Sorry about the mess. So two numbers that multiply to negative 15 add to negative 2. I think that's going to be a negative 5 and a positive 3. But just like before, you want to go back and divide by a. But in that last example, when I divide by a, it doesn't change. It's still a negative 5. It's still a positive 3. So my two factors, that's a negative 5. So it's going to be x minus 5. That's a positive 3. So it's going to be x plus 3. So again, we've got two factors with this problem. And now our last expression, I've got a GCF. Always be looking for that GCF, because just by taking the GCF, I factored it, right? I started off with an x squared. I took the GCF, and now I broke apart that x squared. There are no more factors that I have to come up with. So I've got an x and an x minus 5. So I think the easiest way to come up with this list is to literally just list them out, right? This has an x, this doesn't, this does. So I know my least common multiple has to have an x. This has an x minus 3, this doesn't, but since this first expression had it, it has to be part of my least common multiple. That's got an x plus 3, that's got an x plus 3, but no x plus 3 over here. So I need an x plus 3 as part of my least common multiple. That's got an x minus 5, so does that, but that doesn't. So I need an x minus 5 over here. Plus 3 I already took care of. Minus 5x I already took care of everything else. Let me stress something here though real quick. It doesn't matter if which one only repeated once. This one, x minus 3. It doesn't matter that this first expression only had that x minus 3 because this doesn't have an x minus 3, this doesn't have an x minus 3. But because this first expression has an x minus 3, your least common multiple has to have it. So let's go through and check. Here's our least common multiple. Let's make sure everything that's listed here is here. So I've got an x, perfect. I've got an x minus 3, perfect. I've got an x plus 3, perfect. I've got an x minus 5, awesome. I've got an x plus 3, yep. I already said I have that x right there, and then that x minus 5 is right there. So all 7 of those factors are listed on this least common multiple. All right. So that was part B. Example 3. Example 3, add rational expressions with unlike denominators. So if you remember, we started off with like denominators, then they went to example 2 where it's talking about least common multiples, because that is a step that you have to know how to do in order to add these unlike fractions, unlike denominators together. So I'm going to write this down and then move my book. So for example 3, what's the sum? So you know you're adding these two things of x plus 3 divided by x squared minus 1, and 2 divided by x squared minus 3x plus 2. Again, if you can look at this page and walk yourself through it, this is a great example. It gives you the problem, it sets you up, it gives you different colors for the different factors, it's giving you steps over here, the justification on how it's moving through the steps. That's awesome. I just feel like if we work through it together and do a problem step by step, it's a little bit easier to follow. All right. Like I said, the first step here is you'll want to factor. You want to factor these denominators. I don't care about the numerators. I'm completely ignoring those numerators for right now. I'm only concerned about these denominators. So for my first fraction, if I want to factor x squared minus 1, you can use slide divide bottoms up. In this case, a is 1, b is 0, c is negative 1. So a times c, and then b is 0. Two numbers that multiply to negative 1 and add to 0 are positive and negative 1. Like I said before, your a value is 1. So if I divide those two things by 1, it doesn't change anything. It's still a positive 1. It's still a negative 1. So for my first fraction, my numerator is x plus 3, and my denominator is x plus 1 times x minus 1. And then my second denominator, I'll go ahead and slide divide bottoms up this one. A is 1, b is negative 3, c is 2. So a times c goes at the top, b goes at the bottom. Two numbers that multiply to positive 2 and add to negative 3 are negative 1 and negative 2. But just like before, my a value is 1. So if I go through and I divide both of these by 1, it doesn't change anything. That's still a negative 2. That's still a negative 1. So my numerator was a 2, and my denominator, that's a negative 1, so it's x minus 1. That's a negative 2, so it's x minus 2. All right. I'm going to use some colors, kind of like they're doing in the example problem. But what I want to focus on are all of the factors. In this case, we have 4 of them. I want to make sure that I'm including all of the factors that I have here. So here I've got an x plus 1. Here I've got an x minus 1, and I've also got one over there. And then here I have an x minus 2. So essentially I have 3 different factors, right? These are repeating. So I know that my least common multiple is going to be x plus 1 times x minus 1 times x minus 2. Just because there's 2 of these x minus 1s, I don't need 2 of them. If you put two of them there, you're just going to reduce one out later on. But just kind of keep that in mind. I just need at least one of those in my least common multiple. All right, so if this is my least common multiple, really important to identify, what am I missing in this first fraction from my least common multiple? Again, I'm still not even looking at my numerator. I don't care. Well, I've got an x plus 1. I've got an x minus 1. So the thing I'm missing is an x minus 2. So let me set this up. Like I said, the thing I'm missing in this first fraction is an x minus 2. So just like I did in that first example, I'm going to multiply the top and the bottom by x minus 2. When I multiply the bottom by it, now I have my least common multiple, but keep in mind, I can't just randomly multiply the top or bottom by something. If I multiply the denominator by x minus 2, I have to multiply the numerator by the same thing. Okay. And then my second fraction, I've got an x minus 1, I've got an x minus 2. So what am I missing? X minus 1, x minus 2. I'm missing my x plus 1. So I got to multiply the top and the bottom by x plus 1. So now that I've done that, this is essentially what I have. I've got x minus 2 times x plus 3 plus I've got a 2 times x plus 1. And then my denominator, remember, if I take a fraction divided by an LCM and I add a fraction divided by an LCM, I'm going to be left with a fraction divided by my LCM. So this was x minus 2 times x plus 1 times x minus 1. Same thing with this. This was x minus 2 times x plus 1 times x minus 1. So guess what? This is going to be x minus 2 times x plus 1 times x minus 1. In this case, let me look at this for a second. Okay, I think there's not really going to be kind of a roundabout way of doing this. I think we're just going to have to push through and do some algebra. We started off with x plus 3 and 2 as my two denominators, but keep in mind we had to multiply x plus 3 times x minus 2 because we were missing that from my denominator. We had to multiply 2 times x plus 1 because we were missing that from the denominator. So now what we're going to have to do is multiply everything out, combine like terms, simplify, and hopefully reduce things at the end. We'll see. So if I multiply these two sets of parentheses, x minus 2 times x plus 3, what I'm essentially doing is foiling it out. So x times x is x squared. X times 3 is 3x. Negative 2 times x is negative 2x. And then negative 2 times 3 is negative 6. Same thing with this numerator on the right over here. That's a positive 2. So I'm just distributing it. 2 times x is 2x. 2 times 1 is 2. And then my denominator doesn't change. I'm going to leave my denominator the way it is, and I'll explain why here in just a second. X minus 1. The reason why I'm not multiplying out my denominator, I'm not going to multiply all three of these expressions or all three of these binomials out, is because it's already factored. Nothing is being separated by addition or subtraction between the parentheses. Here, I am adding these two numerators. So what I have to do is multiply everything out, combine like terms. So let's go ahead and do that. I've only got 1x squared. 3x minus 2x is 1x. 1x plus 2x is 3x. Negative 6 plus 2 is negative 4. Then my denominator, x minus 2 times x plus 1 times x minus 1. Now I'm to the point where after I multiplied these all out, combine like terms, now I'm back to a quadratic that I'm going to factor apart and then hopefully simplify here in a second. Let's see. So a times c, that's negative 4. B is 3. Two numbers that multiply to negative 4 and add to 3. I think that's negative 4. Oops, nope. negative 1 and 4. Sorry, I kind of got that a little bit sloppy. Negative 1 and 4, let's double check it. Negative 1 times 4 is negative 4. Negative 1 plus 4 is positive 3. So what I did was I factored out that numerator. It's a negative 1, so it's going to be x minus 1. It's a positive 4, so it's going to be x plus 4. And then my denominator. Now we're to the point, just like we were with lesson 4.3, where you can simplify, where you can cancel out common factors in the top and the bottom. So in the numerator, I've got an x minus 1. The denominator, I have an x minus 1. The numerator, I have an x plus 4, but none of that down below. So my final answer is going to be x plus 4 up top, x minus 2 times x plus 1 in the bottom. And then let's make sure, what's the sum? It doesn't look like they're wanting restrictions. So in this case, that would be the sum. Kind of a long problem. Of course, I showed every single step. So when you're doing this, you might be able to skip a step or two. Maybe you're just going to focus on the numerator and then just write the denominator down here at the end. It's really up to you, whatever you're comfortable with. So, all right. So that was example 3. Let's take a look at 4. Subtract. So this is exactly the same as what we just saw. Looks like my denominators are not the same. So this is exactly like example 3. We've got to find a common denominator, and then we're just going to subtract the two fractions. So let's do that. So the difference, so that means subtraction. Okay. So looking at these, I know I cannot add or subtract fractions if the denominators are different, which they are different. So what I want to do is factor the denominators. However you want to factor, lots of different ways to do it. The way I like is slide, divide, bottoms up, but it's up to you. So for this first denominator, I'll go ahead and factor it. A is 1, B is negative 6, C is negative 16. So AC at the top, B down below. I need two numbers that multiply to negative 16 and add to negative 6. So I think that's negative 8 and positive 2. If I have to divide by A is 1, so it doesn't change anything. So this first fraction is going to be an x plus 1 divided by x minus 8 times x plus 2. Second fraction, still have an x plus 1 up top. And now I'm going to factor that denominator. So A is 1, B is 6, C is 8. So AC at the top, B down below. Two numbers that multiply to 8 and add to 6 are 4 and 2. A is still 1, so if I divide by 1, nothing changes. So that's a positive 4, so it's x plus 4. That's a positive 2, so it's x plus 2. Now we'll take a look, just like we did with that last problem. Looks like both of these fractions have an x plus 2. This first fraction has an x minus 8, and the second fraction has an x plus 4. So just by doing that, I've identified 3 separate factors. So again, my least common multiple is going to be blue, x minus 8, green, x plus 2, and red, x plus 4. Yes, there's another x plus 2 over here. You don't need it listed out again. You already have it right there. So as long as you have 1 with your least common multiple, you're good to go. All right, so what am I missing? This first fraction has an x minus 8 and an x plus 2. So it's got these first two right there. It's missing the x plus 4. So I'm going to have to multiply the top and the bottom. My brain's telling me to do one thing and my hand's doing something else. So I'm going to multiply the top and the bottom by x plus 4 because that's what it's missing. The second fraction, it's got the x plus 4, it's got the x plus 2. The only thing it's missing is the x minus 8. So I'm going to multiply the top and the bottom by x minus 8. Now, if you look at these, you've got the LCM. The x plus 4, x minus 8, x plus 2, x plus 4, x minus 8, x plus 2, x plus 4, x minus 8, x plus 2. They all match. So what I'll have here is my LCM, my least common multiple. The denominator is going to be x minus 8 times x plus 2 times x plus 4. The first numerator is x plus 4 times x plus 1. And then minus the second numerator, x plus 1 times x minus 8. We cannot, let me stress this again. Here's a perfect example. I cannot cancel out this x minus 8 and this x minus 8. Here's the reason why. This x minus 8 is being multiplied by other things. So that would be okay. But this x minus 8, even though it's being multiplied by x plus 1, it's being subtracted from the first set of parentheses. So I cannot cancel out something across subtraction or addition. It's got to be straight multiplication from left to right. So what I have to do at this point is I've got to multiply. I call it FOIL. First times first, outside times outside, inside times inside, last times last. So with this first fractions numerator, x times x is x squared. X times 1 is x. 4 times x is 4x. 4 times 1 is 4. And then my second set of parentheses, I'm subtracting this. So I'm going to put subtracting and then a set of parentheses because I want to make sure I subtract everything. X times x is x squared. X times negative 8 is negative 8x. 1 times x is x. And then 1 times negative 8 is negative 8. So I'm going to go ahead and skip my denominator here, but keep in mind, it's still there, right? There's still a denominator there. I just want to save some ink, save some time. So if I combine like terms, x plus 4x is 5x. So I have x squared plus 5x plus 4. But here's the thing that tends to trip people up. I am subtracting everything in this set of parentheses. I'm subtracting the x squared. I'm subtracting the negative 8x. I'm subtracting the x, subtracting the negative 8. Everything gets subtracted. So I'm going to go ahead and combine like terms first. Negative 8x plus x is negative 7x. And now I'll go ahead and kind of distribute that negative 1. So I've got my x squared plus 5x plus 4. Now I'm subtracting x squared. I'm subtracting negative 7x. I'm subtracting negative 8. All right. And then I think I'm ready to combine like terms and then simplify. So I've got x squared minus x squared. They just get rid of each other. That's kind of nice. 5x plus 7x, that's 12x. 4 plus 8 is 12. And then I have my denominator. And then I think between these two terms, I have a GCF. So I'm going to go ahead and factor out a 12. And now I'll go ahead and write my denominator. So my denominator was x minus 8, x plus 2, x plus 4. Does anything cancel out? Well, there's a 12 up top, no 12 or no multiple of 12 down below. There's an x plus 1 up top, no x plus 1 down below. So nothing is actually going to simplify out here at the end. That would be my final answer. Let's make sure this is the case in the book. Yep. I just always like to make sure I didn't misread something or do something wrong. All right. Oh, and in this example, I'm just noticing it didn't say it specifically in the instructions, but down here it is saying what x can't equal. We talked about that in the last couple lessons. Just keep in mind, x can't Whatever you want to exclude here, you have to exclude it so your denominator will never be 0. In this case, I actually didn't simplify anything out, so I can look down here at the bottom. I would have to state that x cannot equal 8 because 8 minus 8 is 0. I'd have to state that x can't be -2 because -2 plus 2 is 0. And that x can't be -4 because -4 plus 4 is 0. So I didn't see where they said state the domain restrictions, but they did in the example, so I figured I'd talk about it. Find a rate. There's a formula when you're doing rates, and I think they're going to give it to you. Oh, yeah, right here in the notes. Remember that distance equals rate times time. I usually say it the other way, rate times time equal distance. You can also manipulate that equation. Instead of saying you're multiplying rate and time, I can solve it for different things. So if I wanted to solve it for time, I can divide both sides by rate, and you could get something like this. If I wanted to solve that equation for rate, I can divide both sides by, by time, and then I get time equals distance. I'm sorry, rate equals distance divided by time. So you might have to manipulate that formula just depending on what you're trying to solve for. So Leah drives her car to the mechanic. She then takes the commuter rail train back to her neighborhood. The average speed for the 10-mile trip is 15 miles per hour faster on the train. Find an expression for Leah's total travel time. If she drove 30 miles per hour, how long does this take? So they're essentially coming up with a table here to plug in some information, talking about the total distance. It doesn't matter if she uses her car or the train. If the total distance is 10. But they told you up in the problem that the train runs 15 miles per hour faster. So with her car, they just have R for rate. We don't know how fast. It's just saying R. But then the train is going to be R plus 15 because the instructions said they're running 15 miles per hour faster. And then the time, again, in this case, they're trying to solve for time. So they took that formula, and let me go ahead and emphasize what they're doing here. The formula is distance equals rate times time. And I can write that as D equals R times T just for the sake of, for the sake of saving ink. If I have a problem that's asking me what's the distance, bam, I'm good. I'm already solved for distance. If I have a problem, I think like in this one, right? They're asking me for time. How long did this take? So I need the time. So what I can do is I can divide both of these sides by R. The right side would simplify down to just T, and the left side would be D divided by R. So now I have that same exact formula that it's solved for time, and I can just plug in the information. I could plug in the distance, I could plug in the rate, and it'll tell me what the time is. And then the other way, obviously, if you have D equals R times T, this is solved for time. If I wanted to figure out what the rate was, I could divide both sides by T. The T simplifies out on the right, and I get that the R, the rate, equals distance divided by time. So you've got three equations here. All three equations are exactly the same. They're just solved for a different piece of missing information. All right. And this is what they're doing. They're just taking that information and plugging it in. So total time for the trip, 10 over R, and they're getting this straight from this table. That's where all this information is coming from. So the trip, if you keep in mind that she took the car and the train, right? She took the car, to the mechanic and then the train back. So that's why they're adding those two times together. The car time and the train time added together. And then the time equals distance. So 10 times R plus 15. So this is coming from, where are they getting these times? 10 times R plus 15. Okay, so that's going to be the commuter train. 10 times the rate, so distance times the rate. Okay, I was looking at that for a second, thinking that this was the entire equation. But now after I kind of take a step back and I look at this, this is just accounting for just the time. I didn't look at the next page where they start talking about driving rate and other pieces of information. So this work right here is only talking about the time. So there's the time for the car straight from the table. They're adding it to the time for the train straight from that table. And what they're doing over here is finding a common denominator, doing the math, everything we've already done to get that expression down here. I was looking at that and I was like, how are they getting this information from that table? Because that's not time equals distance divided by rate. So it just kind of threw me off what they were doing. So let me walk you through this. I want to make sure you understand how to do that. So in this case, they're only looking at time. That's all they care about. And this is the time column right here. And all they're doing is adding the two times together to figure out how long it's going to take her to go drop her car off and take the train back. So my two times are 10 over r, and they add that to 10 over r plus 15. So we'll go ahead and do this together. It's almost there, right? There's just a 15 over with the second fraction. But remember, you have to have common factors down below. So don't think that I can just add 15 to this side and then have r plus 15 and r plus 15. In a case like this, where you have a binomial down at the bottom and a monomial like this, the easiest way to do it, to set up your least common multiple, is just to multiply the two denominators together. So the first denominator is an r, the second denominator is an r plus 15. Once you do that, you're guaranteed to have that least common multiple. I always say least common denominator. Same thing though. So that would be, once I multiply those together, that would be my least common multiple. So just like we did before though, what is this fraction missing? It's got the r, it's missing the r plus 15. So I would have to multiply this fraction by r plus 15 over r plus 15. This fraction has the r plus 15, but it's missing the r. So I would have to multiply this fraction by r over r. So my denominator is going to be r times r plus 15. We already know that because we found that least common multiple. And all we did was just multiply the two denominators together. We just butted them up against each other and multiplied them. So across this entire numerator, we'll have r plus 15 times 10. And then plus, because I'm adding these two fractions, 10 times r. So I'll just write that as 10r. And then remember at this point, you're going to leave the denominator alone. The only thing you're multiplying out, adding like terms, any of that kind of junk, the only thing you're doing is just with the numerator. So I'll go ahead and distribute that 10. So 10 times r is 10r. 10 times 15 is 150. And then I've got the 10r over here on the right. And again, just to save some time, I still have that denominator. It's still there. I'm just not rewriting it. If I combine like terms, 10r plus 10r is 20r, and then I add that to 150, and then I still have that same common denominator. And then I think up here, I do have a GCF I can take out. What's that going to be? It's not going to be 20. I think it's going to be a 10. So if I GCF out of 10, I'll have 2r plus 15, and then now I'll write that denominator, r times r plus 15. Nothing can cancel. There's a 10 up top and r down below. I can't cancel that. These two parentheses aren't exactly the same, so I can't cancel that. This is basically the expression that I'm going to use to represent time. Let's make sure that that went right. Yep, same thing. They just didn't GCF out the 10. They got 20r plus 150, so that's okay. If we need to multiply it back through for some reason, we will. But I always like to simplify it as much as I can. So then at a driving rate of 30 miles per hour, you can find the total time. So all they're doing is taking that time equation, that time expression, and they're plugging in 30 anywhere they see an R. So you'll notice that's the expression we have. They're just plugging in a 30 and getting a number. So let's go ahead and do that as well. So I'll have 10 times 2 times 30 plus 15. And then it'll be 30 times 30 plus 15. And now I can simplify. 2 times 30 is 60. 60 plus 15 is 75. 10 times 75 is 750. Down below, start inside the parentheses and work yourself out. 30 plus 15 is 45. 45 times 30. I'm going to cheat and look over here and see what they got. 1350. 1350. So 750 over 1350. This can reduce. I've got zeros on the end, so I can just drop a 0. They're both end in 5, 75 and 135, so I can divide them both by 5. That's going to be 15 up top and 5. That would be 27. And then at that point, they're also both divisible by 3, so I'll divide the top and the bottom by 3. That's 5/9. And I think that's it. That's the lowest it can go. So 5/9 is my final answer. So the expression for Leah's total travel time is blank. That's what we found earlier. And the total time is 5/9 of an hour. So 5/9 times 60, that would give you that 33-minute mark. It would take her 33 minutes to go drop her car off and take the train back. Example 6. This example isn't too bad because we've kind of done this before. If you remember back with multiplication and division, when we divided two fractions, we used that idea of keep, change, rearrange. That's essentially what we're doing here as well. So we'll start off with this fraction. Okay. Don't let the two variables fool you, or don't let it throw you off. It's just a different variable. It's nothing too bad. So we want to have common denominators though if we want to add any of these things at the end. Of course, there's different ways you could do this, different ways you could approach this. I'll show you the way that I think makes the most sense to me. I think with my idea is I'll do the keep, change, rearrange thing right off the bat. So I'll keep the numerator exactly the way it is. I'll change division because this is technically the top divided by the bottom. So keep the numerator the way it is, change division to multiplication, and then rearrange this second fraction. So it'll be y over 1. At this point, I can kind of simplify this or at least combine a couple things. With this first fraction, it's going to stay the way it is. The second fraction, you're multiplying those two things. So I'm going to go ahead and just kind of combine that a little bit. So 2 times y is 2y. The denominator, x plus 1 times 1 is just x plus 1. And like I said earlier, you could put parentheses around this if it helps you. For me, I think visually it does, but it's up to you. You don't have to. So at this point now, I'm kind of back to where I started with. You could have started off with just finding a least common denominator up here, a least common multiple for all three of these fractions, multiplied all three of them by that least common multiple, and then move forward from there. I just think it's easier to keep, change, rearrange, flip that fraction in the denominator, multiply it out, and now you're basically back to the examples we've already looked at. In this case, this is exactly like example number 5. You've got two denominators. The easiest way to do it, the least common multiple, is just to multiply whatever they are. This is an x. This is an x plus 1. Bam, I'm done. That's what I'm going to need, both of these terms or both of these factors in this problem. So the first fraction already has the x, it's just missing the x plus 1. So I'll multiply the first fraction by x plus 1 over x plus 1. The second fraction already has the x plus 1, it's just missing the x. So I'll multiply the second fraction by x over x. And here we go. X plus 1 times 1 is just x plus 1. 2y times x is just 2xy. And then my denominators, x times x plus 1, x times x plus 1, x times x plus 1. I know I keep stressing this, but let me say it one more time. I cannot do this. I cannot cancel out those x plus 1s. I know you want to, but you can't, because this x plus 1 is being added to other stuff. This x plus 1 is just being multiplied by x. So technically you could cancel that one out, but you can't cancel this one out because it's being added to something else. So I think in this case, I don't have anything to distribute. I don't have any other like terms. This is just the way it is. I guess I'll go ahead and write it as 2xy plus x plus 1 over x times x plus 1. Nothing common I can simplify out, nothing common I can cancel. And then after I looked at that, I just realized that I made a mistake. So let me back us up to this part right here. When I keep those fractions divided by fractions, I need to keep that the way it is, which I did, change division and multiplication, and then rearrange that second fraction. But what I screwed up on, because I was just going too fast, is I need to multiply the entire numerator by y over 1, not just this second term. I need to multiply both of these by y. It's like distribution. So it's always the learning moment, right? Now I'm set up. Okay, so let's go ahead and do this. So I'm going to distribute that y. So that'll be y over x, because y times 1 is y, 1 times x is x, plus y times 2 is 2y, and then 1 times x plus 1 is x plus 1. Here's the part where we're going to continue. I know that my least common multiple for my denominator is going to be x times x plus 1. This first fraction is missing the x plus 1, so I have to multiply the top and the bottom by it. The second fraction is missing the x, so I need to multiply the top and bottom by it. So my numerator is going to be x plus 1 times y. I'm going to go ahead and simplify that, distribute that y, so it'll be xy plus y. And then 2y times x is 2xy. There we go. That's looking a little bit better. Now, at that point, I'm seeing some common some common things inside my numerator. All three of these terms have a y in them. So I think what I'll be able to do is GCF out of y, and that's going to leave me with x plus 1 plus 2x, and then my denominator. And now I can go ahead and add like terms. I've got an x and a 2x. X plus 2x is 3x. So I have y times 3x plus 1 over x times x plus 1. Woo. Just like before, I don't have anything that cancels. There's a y up top and x down below, a 3x plus 1 up top, but x plus 1 down below. Nothing is common, so I can't simplify anything. All right. Looks like they show you a couple different methods down here, so feel free to look through those and kind of see if one makes sense more than the other. At the top of page 221, it's got the summary of everything that we talked about when you're adding and subtracting fractions. And I think I'm going to go ahead and split this up into part 2. And then the practice, which is on page 222, we'll go ahead and look at that in part 2 of this video tutorial.